Okay, we're recording. So last time we were talking about these characteristics that some functions can have of being onto, aka surjective, and being one-to-one, aka injective. So some functions are one or the other, or both, or neither. And something particularly interesting, though, is when a function has both of these features. We say that the function's invertible. And I want to show you an example of where we can use this. So, it's commonly understood that the square root function is the inverse of the square function. But you actually have to be careful in how you set that up. So this function, this is, casually when people are thinking about the squaring function would think, well, real number in, real number out, whatever. But the problem is, if you set up your domain and target that way, the function is not invertible. Right? So a couple of easy examples. Looking in the target. 25 has two preimages. Right? It is not a one-to-one function. Right? And also, again, looking at the target, -7 has 0 preimages. This is not an onto surjective function. Right? So this function is not even close to invertible as written. What we have to do to make it invertible is we have to restrict the domain and restrict the target. If we consider only non-negative inputs and only non-negative outputs, now all of a sudden this is a one-to-one and onto function. This is an invertible function, therefore, and we can talk about its inverse. And the inverse is exactly what you think it is. What had been the target of this modified squared function is the domain for the square root function, and vice versa. What had been the domain for the modified squared function is the target for the square root function. In other words, the action of taking the square root goes backwards. In other words, from green to blue. Okay, so this then is the inverse. And we have that notation there to represent it. This funny-looking little symbol there that we've all known since elementary school. And that's a shorthand notation for this function, the square root function, which you will notice as we have it defined is never negative. And I commented on that last week or the week before or something like that. Okay, here's another example. The sine function, as typically conceived, as a function that takes real numbers in, gives real numbers out. And again, that function also not invertible and not even particularly close. And of course, you all know what sine looks like. It kind of oscillates up and down, kind of like that. And you can see multiple instances here where it fails to be one-to-one, right? So for whatever that value of y is, there's multiple angles whose sine is that value of y. And for this value of y up here, there are no angles where the sine is that value of y. So again, we have to restrict the domain. And this part, you'll notice, of the typical graph of the sine function, this part does have this sort of nice feature. And for specifically for any value of theta, there is a corresponding value of y. Exactly 1, right? And likewise, for any value of y, correspondingly, there is exactly 1 value of theta. Right? Now you can, question.
Do you need to restrict the target even if the target is only possible with those numbers? Like, could I say those to real numbers because only things in that range will be considered?
That is restricting the target. Right, so the point is, the reason you have to restrict the target is because whatever your target is, that's going to be the domain for your inverse function. And if you're going to have this be your domain, then that square root, that inverse function had better be defined. Yeah. So nothing is, understood. Yeah, it's got to be explicit. Yeah. So okay. So here's then a definition of arcsine. Arcsine is just the inverse function of this carefully restricted this carefully restricted sine function. Right? Arcsine is just the inverse of that invertible sine function. Okay. All right. Okay, now here's a bunch of language. Y'all can read through this. There's nothing deep going on here. The big idea is that if you have a multivariable function, well, you're going to have multiple input variables. And you might have multiple output variables as well. When you're talking about a function being real valued or vector valued, valued is a reference to how many output variables there are. And so if your target is R1, those are real numbers, and so that's a real valued function. If your target is Rm, where m is greater than 1, then those are vectors. That means you have a vector valued function. And then likewise, if you're talking about how many variable, single variable, multivariable, that is a reference to the domain, and whether you have one variable in the domain, R1, in which case you have a single variable function, or maybe you have several input variables, in which case that would be a multi-variable function. So y'all are going to hear me multiple times throughout the rest of this term talking about a vector-valued multivariable function, or a real-valued multivariable function, or a vector-valued single-variable function, this kind of thing. And that's just, terminology to describe what the domain and the target are for the function. Okay, so make sure to read through those details. And again, details about component functions, y'all can read that. So here's an example of a vector-valued, because there's multiple output variables, multivariable, because there's multiple input variables, a vector-valued multivariable function, which sounds very sophisticated and abstruse, but look how completely unimpressive this function is. This is what I like to call the weather function, right? The most trivial of water cooler conversations, right? Talking about the weather. And, well, if you're talking about the weather, you need to know where you're talking about, longitude and latitude, right? You need to know, specifically how high above that point on the surface of the Earth, right? I mean, if you're here in Durham, at the surface, the weather is one thing. If you go up 30,000 feet, it's very different, right? And then furthermore, you need to know what time you're talking about. The weather here in Durham is not constant. It changes as it does everywhere. And so the weather depends on the time. What the answer to the weather function is, the output values of the weather function, well, it may be any combination depending on what you're interested in. Temperature, right? Barometric pressure, wind speed. Is it super windy out? You could add wind direction if you want, whatever. Humidity is a topic of pretty significant interest depending on where you are. I grew up in Houston. It's very relevant in Houston. And so as it turns out, check it out, just talking about the weather, you are describing a vector-valued multivariable function. And I think if you sit down and think about it, you can probably come up with all sorts of examples, ranging from the day-to-day common to more sophisticated, more abstract things. Okay, so let's talk about how to visualize functions. This is going to be mostly a matter of being careful with details. There's not a lot of algebra in this stuff, but what makes it hard is not the algebra. The algebra is easy in what we're about to do. What's hard is understanding the precise meanings of the words that we're going to talk about, and then controlling yourself and preventing yourself from misusing, due to perhaps bad habits from the past, misusing words that going forward we now need to be very careful with. Okay, so we're going to start talking about graphs. I know you all have heard of graphs. Real quick, we'll start with the easy, familiar example that everyone has seen. If you're talking about a single variable function, single variable real valued function. So again, notice that means one input variable, one output variable. Then you write this down, y equals f of x. Right? And the idea there is that this describes an equation which describes a curve in space. Very familiar, I hope. Y'all have seen these pictures a bazillion times. Okay, so notice, though, that a point on this graph does not represent just an input value, nor does it represent just an output value. What we have here is actually a little weird. The input value to the function x is one of the coordinates of that point. And the output value, the y, as it happens here, that y is another one of the coordinates. So a point on the graph has coordinates representing both the input value and the output value. Now, I don't know if you ever really thought of it that way, but that's the construction. You take the function, plug in as many inputs as you want, look at all the corresponding outputs, and for each one, you make an ordered pair, and that ordered pair makes a point in 2 space, and altogether that makes a curve called the graph. How we doing? Hopefully familiar. Okay. All right. So here's a different way you can think about it. We have this function, and given some formula for a function, set the values of the function equal to a new variable. Notice that's how I constructed this equation. Right? I had the function f, whatever that is, setting it equal to y, and studying that resulting equation is how you describe the graph. Okay. All right, so 2 different ways to think about it. Notice the analogous general definition that I'm making here then. So if you have a vector-valued multivariable function in general, right? Then whatever the input values are, those coordinates are the first several inputs, or the first several coordinates of a point on the graph. Whatever the corresponding output values are, however many there are, those output values are the next several coordinates, and all together, this whole thing, notice this point here that we're constructing has n plus m different coordinates. That's kind of weird, right? This point does not live inside of the domain. It does not live inside of the target. It lives inside of a space that we made up just for the purpose of talking about the graph. Right? It's a new space. And the collection of all, that was not good. The collection of all such points is what we call the graph. All right, let's see a higher dimensional example. Explicit higher dimensional example. Here we have a real valued multivariable function. Again, be careful with the language. Real valued. Target is R1. Multivariable, in this case, 2 variable. That means that the domain is R2. And so here's the graph. The graph, again, think of it different ways, but I'm going to think of it here as, well, it's what you get when you set the value of the function equal to a new variable. Now, there were 2 input variables, and so I had to be careful here. I had to use x and y to describe the inputs. So when I set that equal to a new variable, that is now a 3rd variable, and so I'm going to use z. Just, alphabetic order, I guess. Doesn't really matter, of course. But there you go, you have an equation, and we have z equals f of xy. This is an equation in 3 variables. So its solutions are points in 3-dimensional space. And I claim that we're going to get a surface out of this, and I'm going to give you a rationale for that momentarily. But the graph of this function is a surface. What do you think? Everybody happy? All right, so why a surface? Here's yet another way to think about graphs. And let's see here. Think of it as that I've got an input value x, which I think of as representing a point in my domain. Now keep in mind, my domain is one-dimensional. It says so right there. My domain is the real number line. So I've got a one-dimensional list of points. That is my domain. Okay, what does the function do? One could argue, point of view and all that what this really does is it tells you how far does the function push that up to form the graph. Okay. If you have a point x in the domain, you get an output value y, the y tells you how far to go up, and then that ordered pair. In other words, the point you get to by just kind of pushing straight up there is the resulting point on the graph. So, well, no surprise then, because we have a one-dimensional domain, if you kind of take this one-dimensional domain and just kind of little bit at a time in different amounts in different areas, if you just kind of push all those points up, wouldn't you expect to get a one-dimensional graph? So, good general rule of thumb, the dimension of the graph itself, let me clean this up, the dimension of the graph itself is the same as the dimension of the domain. While, of course, now don't conflate that with the dimension of the space that the graph lives inside of is the sum of the dimensions of the domain. Okay. All right, so along those same lines, we have two input variables in this next case, right? Two input variables. We have a two-dimensional domain. If the function is telling us how far to push each one of those points straight up, right? A two-dimensional surface, kind of push it up in different amounts in different places, you would expect to get a surface. Okay, what do you think? Everybody happy with that? All right. Okay. All right, so this is seeming like a reasonable, I hope, reasonable extension of the old, sort of single variable calculus idea of a graph to a higher dimensional setting. But look what is about to go wrong. Let's now entertain the idea of how would we form the graph of a function of three variables. And I want to point out, this is really not a particularly outrageously high multivariable function. I mean, 1 isn't even multivariable. 2 was our very first example of the most simple of multivariable functions. And now, at the second most simple possible case, we have 3 input variables, we have 1 output variable, grand total that is 4 variables. That means that our picture lives in 4 dimensions, and that means that we are out of luck. We cannot draw this picture. Can't draw in 4 dimensions. Right? And there's really nothing you can do about that. And I want to point out, by the way, we could have even seen the writing on the wall a little bit in this last example. Here, 3-dimensional picture, and you see here I've drawn a 3-dimensional picture. But have I really, or did I kind of fake it? Right? I mean, this is a 2-dimensional screen, right? There's nothing back here. It's flat here, right? This is a 2-dimensional picture, but I, am asking you to believe that this diagonal line is actually coming out of the page, right? You're using your imagination there to try to convince yourself that it's actually 3-dimensional. Now, also, furthermore, this looks like a kind of a 2-dimensional surface, but notice, not really. These curves here are just curves. They're lines. I didn't draw anything in here. Your imagination is filling in the blanks here. Right? So I'm already faking it pretty bad just in trying to draw a 3-dimensional picture. 4-dimensional, not going to happen. Somebody had a question. I'm sorry. Was it you? No. Did anybody else? I was right in the middle of a thing, so I didn't want to stop. But everybody good? Okay. All right. So my point here is graphs are very limited in their utility, even in the, I don't want to say the most basic, but even in the second most basic of multivariable functions, out of the question, can't possibly do it. Right? So, it's tough. We are going to have other ways that we can draw pictures that will help us understand multivariable functions, fundamentally different kinds of pictures that are not graphs and whose relationship to the original function are very different than that of graphs. So because of that, it's very important, do not conflate a graph with the function that it's representing. Now, you can get away with this in a Calc 1 class or a Calc 2 class. Single variable calculus, graphs are pretty great. There's really nothing to complain about with this picture. It's a two-dimensional picture I'm drawing on a two-dimensional screen. Perfect. It is a one-dimensional curve that I'm drawing with a one-dimensional pencil. Couldn't ask for a better match there, right? So in single variable calculus, graphs are awesome. Practically every picture you've ever seen in a single variable calculus class is a graph because they're awesome, right? So it is common for students to kind of just figure, all right, well, picture equals graph. Graph equals picture. Not so in multivariable calculus. So heads up, we're going to have several other ways that we're going to represent functions with pictures. Fundamentally different constructions. And you've got to see the distinctions between these different constructions because the geometric features of the pictures will say very different things about the function. And if you use a graph interpretation of a different construction that's not a graph, you're going to get nonsensical interpretations. Okay. All right. Okay, here's the first next way to represent a function. And this is what I like to call the literal picture of a function. I actually have not ever seen this in a book with a name attached to it. It's just, but these kinds of pictures get drawn all the time. I call it the literal interpretation because when you have a function from, let's say, R3 to R1, notice what this picture is that I've drawn here is literally, there is literally a picture of R3. I mean, best I can do, right? And then here is literally a picture of R1. Best I can do. And I'm representing the action of that the function does as an arrow that's intended to suggest literally that points come out of here and then land in here. So it's pretty literal, right? And one could argue that but it doesn't show much. I mean, I can talk about, for example, that I could talk about that, this input point maybe goes to that output point, and maybe I could do a couple others. Maybe this input point goes to that output point, and I don't know, maybe this input point here goes to that output point. I don't know. Right? But, it doesn't really give me a tremendous amount of information. And yet, it is a picture. Right? And, R3 to R1, previously our only alternative was crash and burn. So it's an improvement. It's an actual picture, even if it doesn't seem very useful. Now that said, it is going to turn out this is more useful than it looks. One thing we're going to be doing in this class is entertaining questions such as, all right, I am here at this point, A, and suppose I'm moving with some velocity. Right? So I'm here, and I'm moving that way. And the function that I'm looking at, well, the value of the function was here. As I start moving, though, in the domain, the value of the function will start moving in the target. And so one of the big questions we're going to ask is, what's the relationship between this input velocity and this output velocity? And notice the question is very naturally represented on this picture. Right? And now how we answer the question that's harder, and we'll get to that. It's going to be some time before we get to that, a couple of weeks, I think. But this is a very natural way to represent that very natural question. Okay. All right. Everybody happy? All righty, so moving along. Okay, next one, level sets. Level sets are super. We're going to do a lot of stuff with level sets in this class. It is a very different construction from a graph. When you're looking at a graph, let me go back to the thing here. When you're looking at a graph, you set the value of the function equal to a new variable, right? Again, this is one of a few points of view I gave you on graphs. Graph means set the values of the function equal to a new variable, and you have an equation. Level sets set the value of the function equal to not a new variable, but equal to a constant. Now, that's a very different algebraic choice, right? Very different choice. I'm not introducing a new variable. I'm just saying I'd like to entertain what can I say about when the function is equal to a certain constant. So again, very, very different. And for whatever it's worth, real quick, even though I wrote this as a vector, these output values typically will entertain level sets when the output values are just real numbers. Overwhelmingly the most common thing, certainly in Math 219. I don't want to say exclusively, but maybe almost exclusively anyway. We'll be considering just real valued functions. Okay, so let's get our hands dirty and look at one. Here's an example. You'll notice real valued function, right? One output. Suppose we're looking at this function right here. X squared plus y squared. Now the graph would be a hard picture to draw. It'd be a three-dimensional picture. Three-dimensional pictures are hard. We will talk about how to draw the graph of this three-dimensional picture on the next page. Get there in a minute. But first of all, let's do level sets. And keep in mind, level sets are what you get when you set the value of the function equal to a constant. So this is what a level set looks like. Setting the function equal to various different constants. Okay, so for example, let's look at the output value 1. Notice here I'm setting the value of the function equal to 1. I'm then looking at all the points in the domain for which the value of the function is equal to 1. I get x squared plus y squared equals to 1. And of course we know what that is. That's a circle. Right? Let's look at another output value, 2. Let's find the level set corresponding to 2. So I'll be setting the value of the function equal to 2. So I get x squared plus y squared equals to 2, which again, familiar, also a circle, a little bit bigger. How we doing? Everybody all right? It's a picture. Now, what do I do with this picture? What does this mean? How does this help me understand the algebra of this function? Well, yeah, okay, so we'll talk about that on the next page in just a minute here. But it is a picture, and notice it is a picture that lives in 2 dimensions. It's just a 2-dimensional picture, nice and flat, just like the screen I'm drawing it on. Highly desirable compared to the alternatives. If you were drawing a graph of this, well, okay, now you 3 dimensions. Oh, you're going to have to fake it with the picture. That is, to the extent of your artistic abilities, it's hard to do, right? And yes, it's a skill everybody should practice, and I hope everyone will work on that. And again, I'll remind you, I hope I've mentioned this before, but everything I know about drawing in 3 dimensions, I've summarized in a couple of recordings. It's on my YouTube channel, Miscellaneous Topics playlist. The videos are called Drawing 1 and Drawing 2. A lot of good information in there. If you're not good at drawing 3-dimensionally, I urge you to take a look. But we don't even have to here. I've got a picture of sorts that does give me some information. Exactly what it means, again, yet to be determined, right? But I've got a picture that represents this function. Okay. All right, now let's talk about notation a little bit. Notice that the level set for a given output value is a collection of input values. All right, given an output, we look for all the corresponding inputs that the function sends to that output. In some sense, what we're doing is we're taking the output, where it's like we're kind of going backwards through the function to find the corresponding inputs. Right? And so, with that in mind, the backwardness in mind, F inverse is a pretty common notation to represent a level set. Now, to be fair, this is not a function. One output value might give rise to several input values. We saw that here, right? This output value 1 gives rise to all of these points in red there. That entire circle of points are the level set. But nevertheless, it is kind of going backwards. So even if it's not a function, we kind of steal that notation. Slightly a bit of an abuse, but pretty standard, and it communicates kind of the right idea. Okay. All right. Okay, moving along. So here's an example that I think a lot of you may have seen. If not, we'll kind of talk through the details here. Contour lines on a topographical map. So here's a for example, topographical map showing, let's say, some mountain or a hill somewhere. And the idea of a topographical map is that each one of these lines, curves, represents a given single altitude. So maybe this blue line that I'm drawing might represent, let's say 500 feet elevation. And maybe the green line represents 400 feet elevation, etc. Okay. So with a bunch of these lines drawn, which, by the way, notice they're level sets. These curves. Let me do one again here. Here we go. This curve represents a fixed altitude. This is where altitude equals 300. Wait, what did I say? No, I think I said 400. This is where altitude equals 400. That means this is a level set, right? Equals a constant, aka it's a level set, and it's a level set of the altitude function. So contour lines on a topographical map are level sets. And it kind of does help you get an idea of what this mountain looks like, right? I mean, you can look at this picture here and you kind of can sort of tell, all right, well, there's something really interesting happening there. That's probably the top of the mountain, right? And that sort of thing. And then, by the way, it can also give you advice on how to climb the mountain. And depending on how aggressive you are with your mountain climbing, if that's where you are to start, and here's the top of the mountain that we're going to sort of end at. Notice what would happen if you went straight, as it were, seemingly straight on the map. Notice you're crossing a lot of contour lines over a very short horizontal distance. You're therefore gaining a lot of altitude over a very short horizontal distance. That means it's super steep. Right? When the lines are close together, that means steep. So the smarter move, at least, for a non-aggressive hiker such as myself, don't go straight. Oh my gosh, that's way too hard. Do something like this. Right? And so I still got to the top of the mountain, right? But look how much horizontal distance I've got between passing through different contour lines. Right? There was nothing particularly steep anywhere along that way. That's a much more gentle and enjoyable for me hike. Right? Easier going. Did everybody see the idea? So it's not the same as a graph. It's not like having a three-dimensional model of the mountain on which I can kind of see things. Yeah, that'd probably be nicer. But a three-dimensional model of the mountain probably won't fold up and go in your pocket while you're hiking. And you don't want to lug around a big three-dimensional model of the mountain, right? So a lot of nice features for this being two-dimensional instead of three-dimensional. Is everybody on board? Okay. Here's a real-world example of that. So this is a topographical map of a mountain in Colorado called Mount Evans, which, side note, just in case you're curious, my understanding is that it's the highest paved road in the continental U.S. The paved road goes up to 14,130 feet, and it's a trip. It's so high that your brain doesn't work right. It's very noticeable. It's extremely noticeable. And for whatever it's worth, this road is not in good shape. It's got a lot of potholes and areas where it looks like it's about to crumble off and fall off into, a 1,000-foot drop. There's no guardrails. And again, your brain is not operational at full capacity, so it's very scary driving on this road. I'm pretty sure I'm never going to do it again myself. But if you're looking for a thrill, right, there you go. So what I wanted to point out about this is, notice it kind of follows the rule that we were talking about. If you're there and you want to get up to the top, or at least where the road is, the actual top of the mountain is another 100 and some odd feet up there. But you wouldn't go straight at it. Look, you're cutting contour lines way too fast there. This is going to be extremely steep. Most cars probably couldn't do that. Right? So they do the idea of switchbacks. So notice along in here, they're not going exactly along contour lines, but they're kind of mostly following contour lines. They're slowly increasing their altitude as opposed to going straight uphill, right? And then when it becomes necessary, once you get higher up, say like right here, for example. So again, you don't go straight up. That's ridiculous. You kind of sort of semi-follow the contour lines, but you can't do that forever. You have to kind of switch back, right? So that you keep going kind of just as a whole. You want your approximate general path to approach actually where you're going. So this zigzaggy pattern that they do here, that switchbacking pattern is a way to make it a more reasonable drive, and notice it's level sets that illustrate how this really does keep your slope reasonable. Okay. Yeah.
If you go back to like the previous picture that you had, do you always need at least one point labeled, because what looks like the top could be the bottom?
That's exactly right. So great point. This is one of the downsides of level sets as a way to understand a function. Is the good news, it folds up into your pocket. Bad news, it's not clear if this is the top of a mountain or if this is the bottom of a hole. Technically, just the way this is drawn now. So as you pointed out, one way to address that is you can actually indicate the values of the function, periodically along the way. Every couple of 100 feet, you have a labeled contour line. But depending on how much contour there is to kind of keep track of, even that might not be good enough. And it's a problem. Absolutely. Anybody else? Okay. All right. Okay, so let's see here. Back to it. There is a relationship, very nice relationship between graphs and level sets. Now again, y'all have heard me say this several times already. I'm going to say it several more, I'm sure. Graphs and level sets are different, right? They're different constructions. They give you different pictures that are different dimensional. They're just different in every way, but they are related. So check it out. If you form the graph, you form the graph. Keep in mind, that's what a graph is. Set the value of the function equal to a new variable. The graph of a function of two variables. Versus if you form a level set. Keep in mind, that means set the function equal to a constant. Level set of a function of two variables there. Different equations. But if you take that graph and then do a horizontal cross-section. If you think about it, horizontal cross-section like this, right? You're taking a horizontal slice. That slice, every point on that slice has exact same value of z because it's horizontal. Well, if altogether, if you want to talk about a horizontal cross-section of a graph, that would have you setting f equal to z and then z equal to c. Effectively, you're just setting f equal to c, which is the same as making a level set. So the nice punchline then is that level curves are horizontal cross sections of graphs. And again, horizontal cross sections happening in orange there, and graph happening in green. So I think this is a nice pithy way to keep track of this relationship. Level curves are horizontal cross sections of graphs. And here's an actual example. Level sets of this function x squared plus y squared we've already talked about. There are these circles. Right? Now let's think about the graph of this same function. Keep in mind graph means I set it equal to z. Now we've got to talk about how to understand this equation here. We've got x squared plus y squared equal to z. This will be our first example of taking some sort of weird surface with three variables, trying to understand it. There are some very powerful tools I'm going to show you for this that we probably won't get to today. But just to get the ball rolling first time, notice if you kind of ignore the y, you've got z equals kind of sort of x squared, right? So you would expect this to be parabolic up in the x direction, and then likewise you'd expect it parabolic up in the y direction. And you might expect then as a result that it would look like a bowl as I have drawn here. And that would be correct. Well, again, further details on how to make a more rigorous argument on this will come soon. Okay, so pausing for a second. Again, level sets and graphs, very different. Look how different they are. Right? Very fun, very, very different pictures. Graphs and level sets of the same function, totally different. But they are related. Again, if you take horizontal cross sections, namely you set z equal to c, you slice horizontally through here, then lo and behold, those slices are circles that look just like these circles up here. Okay, to be fair, they live in 3 dimensions and they're sitting up above, right? But aside from the z coordinate that we're not interested in, these circles and those circles exactly the same. Everybody good? All right, so very different constructions, but they're related. Okay, now I'm going to show you an example of how you can use these constructions, I'm going to say sort of backwards. So we had been thinking about, given one function, what are several different pictures that I can draw that represent in their different ways one function. So now we're going to turn that around and say, suppose I have a picture. What different functions can I think of that picture as representing? So one picture, we're going to be looking at this line here, the line L, like that, with this equation there. That line, is it a graph of something? Is it a level set of something? Are there any other things that this is the something of? Right? Any other functions that might relate to this curve, right? In some different way. So the answer is yes, there's actually a bunch of different functions that I can think of this as relating to. So on the one hand, I can think of this line as being a graph. This is a graph. Now it doesn't look like it. You look at this equation, I don't see y equals. But I can play with the algebra a little bit. It's not hard to play with that algebra, and I can just rewrite this as I'll use purple. I'll use black. Solve for y, right? Little easy algebra. Oops, got my colors messed up there. Easy algebra to turn this into this. And notice, having done that easy algebra, now it's written as a graph. Now I literally have a function whose values are set equal to a new variable y. Or said differently, I have y equals some function of another variable. And so this is literally the graph of this function right there. Everybody on board? So that's one example, right? So this picture is a graph. Here's the thing. It's also a level set. Same picture. I don't know why I erased that. Also, same picture, a level set. This is even easier to see because this, as written, already written as a level set, right? I've already got it in the form of some function equals a constant, right? Equals a constant means level set. So I don't even have to do algebra to realize this as being a level set. It's a level set of that function. Same line. Okay. So this same line it's a graph of one function. It's a level set of a different function. Everybody with me? Okay. All right. And then furthermore, same line. I don't know why I keep erasing it. Come on. Same line there. Is parameterized by yet another function. Right? So let's think about what we have right here. Look at this thing right here. And you can see that there's a 0, 2 in there. And then I have t times 3, negative 2, which is that vector. And this is literally a parameterization of the line. So this picture, right, it's not a graph of this function. It's not a level set of this function. It's, you might say that this is the image of this function, but typically what we say is that this is a parameterization of this line. But anyway, punchline, I've got 3 different functions. Right? 3 different functions that relate to the exact same line by way of these different constructions. Now, the reason this matters, when we start learning calculus, which I know we haven't really gotten to yet, but we will very soon. When we start learning calculus, we're going to find that different kinds of derivatives will relate to the picture in different ways, depending on whether are you looking at a graph of the function at hand? Are you looking at a level set of the function at hand? Are you looking at a parameterization? What's the connection between algebra and geometry in your construction? Calculus will be interpreted differently in all of those cases. So, for example, here's an old fact that we know from Calc 1, right? And that is the slope of the curve is the derivative of the function. And easily confirmed in this case, you can take the derivative of this function, you get negative 2/3. You can look at this picture and see the slope is negative 2/3, exactly as predicted, right? So the slope is the derivative of the function. But we have to be careful. That's only true if the connection between the function and the picture is that this is the graph of that function. This whole business about slopes, derivatives being slopes, only for graphs. Specifically and only for graphs. And if you were to make the mistake of thinking, oh, well, here's a function and there's a picture. Let's sweep under the rug what kind of picture it is. Picture and function. So I guess the derivative of this function must tell me the slope of this picture. And it doesn't. In fact, to be precise, we have not yet covered how to even talk about derivatives of this function. But when we do, we find that there is a derivative that we can write down for this function. It's not the slope of this line. It's just not. So the way I like to say this is that we have a calculus of graphs, namely these algebraic constructions like derivatives and stuff, second derivatives. These algebraic things, those get interpreted in geometric ways, in certain ways, by way of the graph construction. We're going to have a whole new calculus of level sets. And we're going to have a whole new calculus of parametric curves. Anyway, very important to keep these things distinct. Which, by the way, I did just now talk through all of this. So I'm going to declare us done with page 6. Y'all have a good weekend. See you later, and see you on Monday. Yeah.